Welcome back to another YouTube live session. Tonight we're going to be talking about Taylor series and a little bit of how to graph some parametric curves, how those things work and whatnot. So without further ado, if you have any questions, oh by the way, please on the right hand side there's a chat box, ask them and I'll be happy to do my best to answer them. So we have the Taylor series for f of x centered at the given value of a, where we have a function f of x equals 1 over x. So what is a Taylor series? And that's the big question here, the big to-do. What the heck do these things look like? So basically what we want to do is we want to represent this as a power series with some special properties. So Taylor series usually looks like the summation n equals 0 to infinity. And you can derive this, it's actually not too bad. It's the nth derivative at the point a divided by n factorial, and all that is times x minus a raised to the nth power. And so the whole trick to a lot of these problems, and if we're trying to find the Taylor series, if we don't have any information prior to, if we're trying to find that Taylor series, we need to catch a pattern on the derivatives. Okay, so first we need to kind of write down some derivatives. So we have f of x equals 1 over x, or this is also x to the negative 1. So that means f prime of x would equal, the easier derivative would probably be writing this as negative x to the negative 2, which equals negative 1 over x squared. Okay, f double prime, bring down that negative 2, so notice you get 2x to the negative 3, which equals 2 over x cubed. If we take our third derivative, we'd get negative 3 times 2 times x to the negative 4, which equals negative, and I'll write it as 3 times 2 all over x to the 4th. And we can do our fourth derivative of x. Notice that would become positive, so we get 4 times 3 times 2 times x to the negative 5th, and then this equals 4 times 3 times 2 all over x to the 5th. Now you may be asking, well, why aren't you simplifying? And the reason why is we're trying to catch a pattern here. And so we want to find all these values when a equals negative 3. So, and see if we can determine what the pattern is going on here. So the first one, notice we get 1 over negative 3, or negative 1/3. I'll rewrite that as just negative 1/3. In our second term, notice when you square negative 3, it becomes positive, so you get another negative, and then this 1 over 9. On our second derivative, we're cubing it, so it becomes negative once again, so we get negative, oh, and let me actually rewrite this, rather than 9, just so we can see it a little better, we'll write it as 3 squared. The next one will get negative 2 over 3 cubed. The third derivative, what do we have? Well, we'll have, notice the fourth power would be positive, so we still have that negative symbol out in front. 3 times 2 over 3 to the 4th. And the fourth derivative of negative 3 would be, well, notice that negative will come back into play, so we have negative, and then it goes 4 times 3 times 2 times 3 to the 5th. And we can keep on going from here. Well, the main goal, what we want to obviously try and find, is the nth derivative of negative 3. So how can we start to describe that? Well, let's start to see what happens, and hopefully we can see an easy part of the formula and a harder part of the formula later on down the road. So the easiest part, notice all these symbols are negative. So we'll put a negative symbol right out in front, and then we have our fraction. And so notice when we have the 0th derivative, so there's no derivative, it was 3 to the first. When there was the first derivative, it was 3 squared. When it was the second derivative, it was 3 cubed. When it was the third derivative, it was 3 to the fourth. When it was the fourth derivative, it was 3 to the fifth. So you might think it's initially 3 to the n. But notice, for example, when we have n equal to 4, so if we have this value right here, that corresponds to 5. If we had the 3, that corresponds to 4. So technically what we need, in order to get there, we need to add 1 to that value. And so that's part of catching these trends, is just kind of going through that. Now the next part, in the numerator, that might be a little bit trickier. So we have to be a little bit more creative here. In terms of what we have, what I'll do is I'll write this 4 times 3 times 2. We can multiply that by 1, and we all of a sudden have negative 4 factorial over 3 to the fifth. In the same regards, we have negative 3 factorial here over 3 to the fourth. And in this one, we have negative 2 factorial over 3 cubed. Now here's where it gets a little bit more interesting coming up. So we'll have negative 1 factorial over 3 squared. So what can we write this top one as? Well, there's a little trick that we need to remember, that 0 factorial also equals 1. And so we could rewrite this. Notice for every single derivative you have whatever that derivative is, that you're taking the factorial involved with it. So this would be n factorial sitting up on top. So our formula for 1 over x, according to this Taylor series idea, we'd have negative, for the nth derivative of a, it's negative n factorial over 3 to the n plus 1, and then all of that is over n factorial times x minus, and then we have a is equal to negative 3, so x minus negative 3, and then that's raised to the nth power. So, oh, and I need a summation out there, that's the important part. So all of this, if we simplify, notice we can actually cross off some stuff. The n factorials cancel immediately, and what we're left with, and we'll pull that x plus 3 to the n on top. So summation n equals 0 to infinity. We have a negative, and then it goes x plus 3 raised to the nth power, all over 3 to the n plus 1. And we have our solution. So in terms of our Taylor series, 1 over x, that function would equal this. Now, the real question is, how often does it equal? For what interval? Are these equal? And that would take a little bit of work, but not too bad. You could end up using, for example, you could use your ratio test, and you could solve that pretty quickly and get down to your final answer. So go ahead and try that, see what that interval is, and then you'll have when these two actually coincide or are equal for those values. And it will be an infinite range of values, but not always. Your radius of convergence will not be infinity in that case. In the next one, you may have seen a Maclaurin series for this one, and that's when a equals 0 is a Maclaurin series. But so remember, once again, we have our Taylor series, what we're looking for. So this is summation n equals 0. If we don't know what it is off the top of our head, we can start to work with it. So this is the nth derivative of the point A, and then we have over n factorial, and then it goes x minus a to the n. So we need to start to work with derivatives here. So f of x equals sine of x, f prime of x equals cosine x, f double prime of x equals negative sine of x, f triple prime of x equals negative cosine x. And then when we have the fourth derivative, we've cycled back around. I'll actually write down a few more. But notice this is going to have a repeating sort of nature. And so our next one, negative sine of x, 7th derivative is negative cosine x, 8th derivative is positive sine of x again. Okay, so hopefully you can catch that pattern in the derivatives. And now what we want to do is we want to find f of pi. Well, that's going to be sine of pi, which is negative 1. F prime of pi, well, cosine of pi is 0. And f double prime of pi, well, that's negative sine of pi, so that's negative 1, which equals positive 1. Okay, so then f triple prime of pi would be back to 0. And f, the 4th derivative of pi would be back to negative 1. The 5th derivative of pi equals 0. The 6th derivative of pi, notice that would be back to positive 1. We just kind of cycled around. So 7th derivative of pi equals 0. And the 8th derivative of pi equals negative 1 again. So notice, if we're writing out sine of x, this is supposed to be f of pi over 0 factorial x minus pi to the 0. And then we can continue f prime of pi over 1 factorial x minus pi to the first plus f double prime of pi over 2 factorial x minus pi, the quantity squared, plus f, that's a 3rd derivative. Let me write it this way. Over 3 factorial x minus pi, the quantity cubed, plus the 4th derivative at pi over 4 factorial x minus pi to the 4th, plus so on and so forth. Well, what does this equal? Well, notice what happens when you have an odd one. This whole thing is 0. So that means that piece is gone. Well, in this odd one, that whole thing is 0. So that means this whole piece is gone. So what do we have? Well, we have 1 over 0 factorial x minus pi to the 0 plus, well, our next term that we have that's positive, or I'm sorry, I wrote positive 1, it's negative 1, plus then we have positive 1, my apologies for getting that mixed up, x minus pi squared, right? And then we skipped another odd term because all those odd derivatives will be cosine of pi is involved, and that means it's 0. And then so our next one would be negative 1 over 4 factorial x minus pi to the 4th. And if we wanted to keep on going, you could get positive 1 over 6 factorial x minus pi raised to the 6th, plus so on and so forth. So what's happening? Well, first off, we got to think of a clever way to kind of write this, where it goes negative, positive, negative, positive. Well, so the way to do that, you got to alternate negative 1. Well, if we put negative 1 to the end, notice when it equals 0, that would be positive 1, then negative 1, positive 1, then negative 1. Well, we wanted to go negative, positive, negative, positive. And so the way to shift that just slightly is go negative 1 to the n plus 1. And we've taken care of that piece. Okay, so that part's not too bad. Now, the other piece is involved. We'll have, and I can put that, we'll put the 1 up top here. So notice we go 0, 2, 4, 6. Right? So if we put n, notice that would go 0, 1, 2, 3. Right? So what we want to do each time is we want to multiply each of those numbers by 2 because they're all even numbers. So 2n, and then we'll put a factorial, and notice that matches now. So we go 0, and then 2 times 1 is 2, which matches this term, and then 2 times 2 is 4, which matches this term, and 2 times 3 is 6, which matches that term. And the exponent should be the same, so it just goes x minus pi, it should be 2 to the n. And so this happens to be our power series for sine of x when x equals pi. When not x equals pi, when our a value equals pi. So the other thing, other comment, check the interval of convergence. Or for the radius, that does just enough to tell us what's going on here. Check for the interval of convergence, and that'll tell you even more for information in terms of where these things are actually the same, right? That's the main idea of what we're trying to get at. So speaking of main ideas, a lot of these are worked out for you, and so that's what I want to kind of mention. So first off, you saw some actually in the power series section as well. So like natural log 1 plus x, we could figure that one out. The main 4 that we're going to look at, so first off, the sine of x equals the summation n equals 0 to infinity of -1 to the nth power x to the 2n plus 1 over 2n plus 1 factorial. So notice what we've changed. A Maclaurin series has a equals 0, right? So every time our a equals 0, that's a Maclaurin series. Before, what we were doing was just a regular Taylor series where a equals pi. So a Maclaurin series is just a special type of Taylor series. That's all there is to it. And the sine of x, notice it's all the odd powers is all we're dealing with. Okay, so all the x to the odd power. So, and you can see this is x minus 0 to the 2n plus 1. That's what's happened there. If you take the derivative of the sine of x, notice you should get cosine of x, and you can take the derivative of this x to the 2n plus 1 over 2n plus 1 factorial, and you'll get what's down below. Okay, so that's how we actually prove that result. So you get the summation n equals 0 to infinity of -1 to the n x to the 2n over the quantity 2n factorial. Now the interval of convergence on all, actually this and the e to the x, is for all x. And that's a beautiful thing right there. So that means no matter what value of x you're using, these will be identical. So what we can start to do, the beauty of Taylor series is maybe we want to write the first 5 or 6 terms. And you'll start to see the behavior of sine of x when we're in a real close range. And so this up and down behavior, it gets closer and closer the more terms we write out. But basically we can approximate sine of x, cosine of x, e to the x, all with polynomials. So the cosine of x, you have that one. The e to the x, that's kind of the big one that we start with usually. That's the summation n equals 0 to infinity of x to the n over n factorial for all x. And then to see one where it doesn't have the interval of convergence being all values, arctangent of x, for example, is summation n equals 0 to infinity, -1 to the n, x to the 2n over 2n plus 1 for all absolute value of x less than 1. That means the radius of convergence actually equals 1 in that case. So there's a few values. Let's see how we actually work with these things. What do they do for us? It might seem like a whoopity freaking do, right? So if we look at x cosine of 1/2 x squared, what the heck goes on? Well, we know that cosine x for all the x values, this equals a summation n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial, right? So that means when we write x cosine, oh, and by the way, where did that come from? Well, it just came from the previous page. If you notice, we're just using this formula right there. Okay? So this is x cosine of 1/2 x squared that we're looking at. So what do? Well, we took this summation and we're multiplying that whole summation by x. And now we have summation n equals 0 to infinity of -1 to the n. But we no longer have an x on the inside. We have a 1/2 x squared. So that's a simple fix, really. You take a 1/2 x squared, put it in wherever you see an x, and so that's what you get. So this becomes 1/2 x squared raised to the 2n power, and then this is 2n factorial. So we can simplify this thing a little bit. We'll leave the x out for now. And this is the summation n equals 0 to infinity, -1 to the n. Now we have 1/2 raised to the 2n. Well, we can write that as 1/2 squared raised to the n. And then we can write x squared. We can square that and then raise that to the n as well. And that might make it look a little nicer for us. And all this is over 2n factorial. So now we can rewrite our summation n equals 0 to infinity. We have -1 to the n. We'll have 1/2 squared is 1/4, and so that 4 will appear down below, but it'll be 4 to the n because of that extra n being applied there. We'll have a 2n factorial still sitting down there. And then x squared squared is x to the 4th. And then that's raised to the n. But what we want to do is this is x to the 1st that we got to multiply on in there, so that what that does is that adds an extra component of 1. And so that would be our final answer in terms of what we're looking for rewriting this. So notice we can take something that looks real complicated, and granted this series, don't get me wrong, they do look complicated, but we can write it as something that we might be able to work with and make our lives a little easier. And you'll see how this works in just a little bit. So for the arctangent of x cubed, once again, so kind of just referring back, this is, if you notice, is a summation n equals 0 to infinity of x to the 2n over 2n plus 1. So we have x to the 2n over 2n plus 1 is what we're looking at. Oh, I'm sorry, I actually made a mistake here. I was thinking about that for a second. This should be x to the 2n plus 1 when you take that antiderivative. So real quick, that's x to the 2n plus 1 over 2n plus 1. And so, yeah, good thing we double checked that here. So arctangent of x, sorry about the little writing error before, summation n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1, and I put the -1 to the n just in another location. That's not going to be a big deal. That's going to stay off to the side, and we'll work with that when the time comes. Okay, so what happens, right? Well, if we want arctangent of x to the 3rd, notice what that does is that replaces, and I'll put the -1 to the n in the correct spot now. Or it's all correct, but it's just a more familiar spot, I guess I should say. So you have x cubed to the 2n plus 1 all over 2n plus 1. And so this whole thing equals the summation n equals 0 to infinity of -1 to the n. And notice that becomes, you got to distribute the 3 to both parts, so that's x to the 6n plus 3 all over 2n plus 1. And you are done. Okay. So hopefully, I don't see any questions on that. If you do have questions, please let me know. And we can move forward. F of x equals x cubed e to the x squared. So first off, we have e to the x equals the summation n equals 0 to infinity. This is the nice one for us. It's x to the n over n factorial. It's kind of our bread and butter one that we use oftentimes. So x cubed e to the x squared. Notice that we can write x cubed times the summation. Okay, well, what's our summation that we're going to deal with? Well, we have e to the x squared, so that means we're going to replace x with x squared. So that's x squared to the n all over n factorial. So that thing, we can bring the cube, x cubed onto the inside. But remember, this becomes x to the 2n, and then when you have times x cubed, that becomes plus 3 up top in that exponent all over n factorial. Okay, so now our last one, I tossed this one in here because it's kind of interesting. So the original intuition might be sine of x equals summation n equals 0 to infinity of -1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. And so what some people might think is, okay, so sine squared of x equals, well, this should just be, let's write it this way, sine of x, the quantity squared, which that should just be the summation n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial, and then we're going to take that and square it, right? And that sounds hunky-dory, but I just want to illustrate what's going on here. So notice our first term, when we plug in 0 to all these, you're going to get 1. Then you're going to get minus, when you plug in 1 to all those, you'll get negative is where we have minus, but then you'll have x cubed over 3 factorial. Then plus, plug in 2 and you'll see it's x to the 5th over 5 factorial. Then you get minus x to the 7th over 7 factorial, and then plus, and notice that's a infinite sum right there, and if we're to multiply that on out, we have 1 over x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so on and so forth. So we have an infinite product. That does not look nice, and you don't want to do that multiplication. That wouldn't be fun at all, right? So hopefully there's an easier way, and luckily there is, and it's understanding your trig identities. So really the best method to kind of approach this with is take 1/2 and then go 1 minus cosine of 2x. So what the heck does that look like, right? So we'll have the 1/2 and then we'll go 1 minus, well, cosine of 2x, if you remember cosine, we just take the derivative of this, so we'll reduce the power, and then we'll change, it'll basically become the 2n plus 1 would cancel with the 2n plus 1 on the bottom, and you're left with negative 1 to the n, and then it goes x to the 2n over 2n, that quantity factorial. So that means this is, when we plug in 2x, it goes summation n equals 0 to infinity of, now you have x squared, oh, sorry, not x squared, 2x raised to the 2n all over 2n factorial. We can close that off. We get 1/2. This is a, actually before we do that, we can rewrite this as 1 minus. What's our first term? Well, our first term, if you plug in n equals 0, notice you get the 0 power over 0 factorial, so 2x raised to the 0 power over 0 factorial, that's just 1. And then, oh, I forgot the negative 1 to the n. Okay, so we can go minus 1 and then plus, well, let me write it this way, the minus the summation, because we have to, so I pulled out the first term, but so now let's start it at n equals 1 to infinity, negative 1 to the n, and then this would become 2 to the 2n, which is just 4 to the n, and x to the 2n, all over 2n factorial, right? Okay, so moving forward from there, notice your 1's would cancel. You have that 1/2 times negative whatever this is, right? So that makes 1/2 times, we can bring that negative 1 in, so you get summation n equals 1 now to infinity, negative 1 to the n, and then 4 to the n, or you could write it 2 to the 2n, that's fine too. X to the 2n, and then we have a 2n factorial. Bring that 1/2 now on in, and we'll be in good shape. So this thing becomes a summation n equals 1 to infinity. Notice negative times negative 1 to the n becomes negative 1 to the n plus 1. Get 4 to the n, x to the 2n, all over 2 times 2n factorial. Okay, so now we have it all in one sum. That's kind of our main goal when we're doing this stuff, so we're in good shape there. Alright, we're rocking and rolling here. So what the heck do we use all this stuff for? Well, hopefully you remember integrals like this. Not fun. We could try integration by parts, we could try substitutions, things like that, see where it takes us. It might not be a fun place where it takes us. So, what do we actually do? Well, we don't try and do that. I'll get out of there. Okay, there we go. So in this case, what we try and do is we rewrite this. We know that this is equal to this x to the 9th. Well, we can rewrite this as a summation. N equals 0 to infinity. What's sine of x to the 4th? Well, an easier way for us to rewrite that one would be, we have the negative 1 to the n, x to the 4th to the 2n plus 1. And then we have all over 2n plus 1, the quantity factorial. Oh, let's go in black. So notice this makes x to the 8n plus 4. And when we bring that x to the 9th to add it on in, this whole integral becomes the integral of the summation n equals 0 to infinity of negative 1 to the n x to the 8n plus 13 all over 2n plus 1 factorial. So, oh, and we need a dx here and a dx here. Integrals and summations, remember, you can move things around. The only thing that has an x involved is the x to the 8n plus 13. So we can rewrite this summation, n equals 0 to infinity. You have a negative 1 to the n over 2n plus 1 factorial. And then it's just an integral of x to the 8n plus 13 dx, which freaks some people out, and understandably so. But don't let it freak you out. It's just, we're reversing the power rule here. So this thing becomes summation, we don't have any changes with the negative 1 to the n, and then the 2n plus 1 factorial. And then so now all we need to do is add 1 and put it over that number. So this becomes x to the 8n plus 14 after we add 1 and put it over that same number, 8n plus 14. And don't forget to add that constant c. And this, folks, represents our indefinite integral. Okay, so hopefully you see how that can cut down on time, drastically cut down on time. It can even allow us to solve integrals that you couldn't solve before. So this integral actually equals, and you can try this as much as you want, you don't have the tools to do this without power series. So this is x squared times the summation n equals 0 to infinity, and it's usually x to the n over n factorial, but since we have a negative x squared up there, we'll put a negative x squared to the n over n factorial, and then we want a dx. And so this whole thing equals the integral of the summation n equals 0 to infinity. So notice we have that negative x squared, so that makes it negative 1 to the n. And then we'd have an x to the 2n, but then we add in that 2 from this moving on in. And then all this is over n factorial, and we have a dx. So moving that around with the summation, remember the only thing we're integrating with respect to is the dx. So we're integrating with that respect to that x. Notice negative 1 to the n does not have an x involved. N factorial does not have an x involved. So the only thing that does is x to the 2n plus 2 dx. So same rule, and that's the beauty of these. The rule is actually quite simple. And we can do all our integrals, because this is defined on all real numbers, we're good to go here. We don't have any problem points or anything like that. And you can double check to make sure that the domain of this thing would stay the same. That's not too hard. And so what we end up with at the end of the day is that beautiful summation. And so this, you can try integration by parts, you can try all sorts of substitutions. Good luck with that. It won't take you anywhere unless you use this power series expansion. So it shows you why we need this stuff. Why do we need this Taylor series? There's a lot of beauty to that part. So now our next one, what are we actually looking at? Well, this becomes the integral of the summation n equals 0 to infinity of -1 to the n, and this would be x to the 2n over 2n factorial. Just I want to double check real quick, make sure I did that right. Did I leave the -1 to the n in there on the sign? Or is it not going to let me go back there? Oh, come on. Okay. Sorry about that. I just wanted to double check to make sure. Sometimes it is natural to forget that -1 to the n in some of these. And I wanted to double check that we didn't do that in that one case. So going back, oh yeah, we were good. We left in the -1 to the n, so we're good. I always like to go back and double check. I know I'm trying to work a lot of problems on the fly, so keep that in mind. So in this case, you might say, what the heck are we doing here? Well, a nice way to break this up, notice you have a -1, so there's nothing real easily done right away. So what we'll do is we rewrite this 1 over x, but let's pull out the first term. So if we go 1 plus, well, this would be the summation n equals 1 now because we pulled out the first term. The first term is 1, you can see when you plug in n equals 0 to all those terms. So the same formula applies, -1 to the n, x to the 2n over 2n factorial. And we'll put that piece in parentheses, but then we subtract off 1. Now, what's so important about that? Well, the fact is that not the dx, sorry. Sometimes that pen has a mind of its own. So the 1's will cancel. And what are we left with? Well, we're left with this integral of the summation n equals 1 to infinity of -1 to the n x to the 2n over 2n factorial, and then all that's times 1 over x. So notice you can subtract that exponent, and since we're at n equals 1, that's fine. That's a legit move. So this is the integral of the summation n equals 1 to infinity of x to the 2n minus 1. Woohoo! All over 2n factorial, and then we have that -1 to the n kind of sitting around, and we need a dx. And we needed a dx back here. Okay. So this thing becomes, oops, let's start with the summation, pull out all the stuff with the n in it. N equals, oops, 1. So it's important on our index to be at the right spot. N equals 1 to infinity, -1 to the n, x to the, oops, not x just yet, 2n factorial, and then the integral of x to the 2n minus 1 dx, and so we add 1. So this becomes the summation n equals 1 to infinity, -1 to the n over 2n factorial, and then this would be x to the 2n when we add 1 with -1, that makes x to the 2n over just 2n, and then we add that constant c. Put that in parentheses and we are done. So hopefully that makes sense on that part. And this leads us into the next section, which we're going to talk about, is parametric equations. And in particular, I want to talk about drawing the graphs of these things. So there's some nice formulas, and oftentimes what we try and do is replace these parameters. And the parameter in this case we're going to call t. There's a couple different ways to do that. So so notice t ranges from -infinity to +infinity. So if I have t on this scale and I have x on this scale, notice what's happening. Well, we get these little values is up and down, up and down, up and down. Now, I should be a little bit more precise, but hopefully I'll be able to get this another way. So notice this first t value where we're going to hit that spot is pi over 2. This spot would be pi. This spot would be 3 pi over 2. And we make a full period at 2 pi. And we can do the same exact thing in terms of doing a drawing for t and for y. Right? In this case, we can go about our drawing this way. And so notice at pi over 2 there, and we're at 1 for the y value. This is 1, by the way, and this is -1. Hopefully that's no surprise there. Same thing over here, -1 and +1. So you can keep on going. You have 3 pi over 2 when the y value is -1, and then you have 2 pi when you made the full period. And so now when we're trying to draw x and y, put our x here, put our y there. Let's think about what happens. So when t equals 0, our x value is 1 and our y value is 0. So just a little FYI, t equals 0 implies, well, our x value is 1, our y value is 0. Okay, so that means on our graph, if we have, say, we went 1, we went 2, we went -1, we went -2, -1, -2, +1, +2. I'm not saying that's to scale, but hopefully you'll get the gist in terms of what's going on. So our first point right there occurs, and this could start when t equals 0. Now notice our next point that's kind of a big one was when t equals pi over 2. T equals pi over 2, what happens? Well, we get the x coordinate is 0. And what happens for the y coordinate? The y coordinate is 1 when t equals pi over 2. So you get this point right here. So this occurs when t equals pi over 2. Right? In a similar manner, we can see, and you can keep on going. You can go when t equals pi. T equals pi gives us what? Well, it would give us -1 for the x value and 0 for the y. And then you can also do, so that's going to put this point on the graph. And then when you get t equals 3 pi over 2, you're going to get 0, -1. Right? And you can check that out. That's not too bad. There's our y value, there's our x value, and so we'd get this point on the graph. And notice what's happening. Well, our x value, this is where it gets tricky. Going from 0 to pi over 2, and let's kind of t equals pi, t equals 3 pi over 2. And then we'll talk about what happens some more. So going from 0 to pi, we have, or 0 to pi over 2, we have the x values decreasing. See how it's falling there? So the x value is decreasing. So that means in terms of our x values, we're going to be going in this direction. Right? So starting from there, we're going back towards the y-axis, and our y value is increasing. So you're going to have it going up in this direction. Okay, so the way we do that is something like this. Okay. And then moving from there, if you go from pi over 2 to pi, notice the x value is still decreasing, so you're going this direction, and the y value is now decreasing, so you're going down. So you get something like this. And then you can keep on going, and I'll erase that piece. From pi to 3 pi over 2, notice the x value is now increasing from that -1 value, so you're going in this direction, and the y value is decreasing, so you're going down in that direction, and so you get something like that. Okay. And last but not least, from 3 pi over 2 to 2 pi, notice you finish back at 1, 0. And that's no coincidence. Whoop, oh, got a little sloppy there. Why is that? So this is 2 pi, and by the way, look what happens. It just cycles over and over again. So what's going to happen is we're going to keep on going in this direction over and over and over again, right? And so for every 2 pi for our t, we're going to make a full revolution on this thing. And this is a circle, a surprise, surprise. And where did it come from? Well, it came from, we could have had an easier way to approach this. We could have just checked out a nice way to get rid of the parameter. Notice you get cosine squared t plus sine squared t, that equals 1. That's just a property of those. So in this case, what do you have? You have x squared plus y squared equals 1. And what the heck is that? Well, we recognize that, or at least I hope we do. This is a circle centered at 0, 0. With radius 1. Now the one caveat though, where one revolution occurs for the intervals for every period of 2 pi. Okay. So now let's check out this one. Notice you can rewrite the same thing. And so that's still a circle going around there. And if you're not checking with these graphs, you might not even consider what's going on here in terms of what's the bigger picture, right? And if you do draw the graphs though, you can kind of go through, they're not too bad. So now for the x value, if you put x up here and t down below, you still get the same up and down motion. And same thing over here in the negative side. But the big difference is when this thing occurs, and when this value occurs, and when this value occurs, and when you get back. So notice the big thing here is when we get to 2 pi, we should be back to 1. So that is 2. So that means this value right here would be 1.5. That means this value right here would be 1. And that means this value right here would be 0.5 or 1/2. And the same thing happens for the y. You can kind of shrink that down so the period's 2. Okay. Notice if I didn't have them both be pi t, it's all bets are off. And we got a different sort of graph we're looking at. So what happens is this thing's going around. But this goes around faster. Than the above graph. In fact, it's going with a period of 2 instead of 2 pi. Right? So keep that in mind. We're going around that graph and we're just going around faster and faster and faster. Okay? So by the time the first one made 1 revolution, you've made more than 3 revolutions in this case, just an FYI. Okay? So keep that in mind and seeing that the graphs might look the same, but what's happening is that could be something slightly different. Okay, so now this one, this looks kind of scary, right? Well, it's not so bad as well. If you look, We can do a little finagling, and notice that most of this we have the cosine t. Let's start to move things over. So we have x minus 4 equals 3 cosine t, and then we have y minus 1 equals 3 sine of t. So we're showing how we can work with these parameters, get rid of them. And so what happens? Well, we can start to do the square of the cosine, square of the sine. So if you go 3 cosine t, the quantity squared, plus 3 sine t, the quantity squared. Notice that equals, you can factor out a 9 because you have 3 squared in both places. So you get 9, and then you get cosine squared t plus sine squared t. And so that equals 9 times 1, which equals 9. So what does that mean? Well, that means you can rewrite the first one as x minus 4, the quantity squared, plus our second term was just y minus 1, the quantity squared. And that whole thing equals 9. So this is a circle centered at 4, 1, with radius, and then we take the square root of that number on the right hand side, and so the radius is r equals 3. And so without even touching the drawings, once again we can start to draw the graph. Now let me do this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, and 4. We'll go down 1, 2. Okay, so we're centered at 4, 1. So there's our center of our circle. And then we want to go radius of 3. So we'll take this point right here. We'll go right to the top there. We'll go right over here. And we'll go right down there. And now we need to just draw a circle connecting all those points. Don't let your eyes fool you, that's a perfect circle. And now you can double check, you can actually do the drawing as well. In terms of you draw the x and t and the y and t and see what happens. If you have t and x, say you have this point in the center of that would be 4. And then you'd have 1 and 7 now. And so you start at 7, drop down to 4, go back up there, and you get something that looks like this. So that's what's going to happen there. And then the points where you cross like 4, that would be pi over 2. When you hit 1, the minimum, that'd be pi. When you get back to the 4, that'd be 3 pi over 2, and so on and so forth. For the other one, for the y value, in terms of t, you're starting at 1 plus 3 sine t, so 1 is kind of your center point. You go up to 4, you go down to negative 2. And in this case, you're going up and down and up and down and up and down. Notice that's not at the same scale for the other. Sometimes it's nicer to draw them right on top of one another and you'll be in really good shape. So we get pi over 2, we get pi, we get 3 pi over 2. And so, oh, I put pi a little too close, my apologies. Pi should have been right about there, so there's pi. But 3 pi over 2 still goes in the same place and whatnot. So you can build this whole graph using this idea, or you can do the replacement and just recognize that the period is going to be 2 pi when we're going around. Okay? So you have a couple different ways to approach this, and you can see though I'm trying to get away from the parameter if at all possible and draw it as long as I can go back and determine what that period is if we have a circle. But do we always have a circle? Well, the answer is no. So there's other ways to kind of handle those problems. Well, if we have x equal to t minus 1, we can try and work with this and solve for the variable t. So you get x plus 1 equals 2t. So that means t equals 1/2 x plus 1. So that means y equals 1/2, and then t is 1/2 x plus 1, right? And then we go plus 1. So notice all of a sudden this makes just y equals 1/4 x plus 1 plus 1. So if we're to draw this graph, hopefully we recognize what this is right away. If not, no big deal. We could start at the point 0, 1, or 0, 1, I'm sorry. 0, let me write this actually just a little bit nicer for us rather than doing that. So this becomes y equals 1/4 x plus 1/4, so that would mean plus 5/4. Okay, so if I have 1, 2, 3, so on and so forth. 1, 2, 3, 4. The really good one would be if I start off with -1, I get 1. And then if I go to 3, for example, I should get 2. So 1, 2, 3, I should get 2. I'm just picking random values here to try and, I'm actually using this equation to find the values, but you can use this as well. As soon as you found one constant that works out nicely, you can kind of go from there. So just plugging in those values though, hopefully you recognize this was a straight line. And this must go forever and ever in each direction because our t values range from -infinity to positive infinity, meaning we can go all over the place. So we can go in either direction. Now, as t increases, notice we're increasing. So if you're to draw the direction of t as we get larger and larger, your t's are going always in this direction, towards that positive infinity line. So that's what happens in this case is we have a line. Now, what was the dead giveaway? Well, when you look at this is t to the first power, this is t to the first power. There's no other trig functions or anything like that involved. And that should be your giveaway in terms of we could recognize that those are always going to be a line, in fact. So you can start to see how some of these can start to build real quick. In a similar manner, this could be recognized as a line. Now here I'll show you another way to do it. If you recognize that this is a line right away, let's make our life a little easier. So if you recognize that this is a line, you go t equals 0. That implies x equals 2 and y equals 3, right? So we go 1, 2, 1, 2, 3. And so that should be a point on the graph. Okay? And you can pick another t value. Let's say t equals -1. Or positive 1, or -1 just looks a little nicer here for us to get to. So notice that would be x equals, if t equals -1, x equals -1. And that means y equals, well, -1 will make positive 1 for the y. So when we go -1, you get positive 1 for the y right there. Now you could keep on drawing and have all those points in there, but at the end of the day we know this is a line because it's t to the first, and it's just x, not an x squared or anything like that, or a y squared. And so if we just connect that line, as soon as we just pick 2 points, done, right, for drawing the graph. And now if we had to come up with an equation for this, notice by the way, as we increase our t values, we're going in this direction. So let me start it from here. This direction is the direction we're going. As our t values increase, we are going more and more towards positive infinity. Now, kind of going through this, how do we actually fix that and figure out what the values are? Well, you can solve for t in that first equation. So you get x minus 2 equals 3t. So t equals 1/3 x minus 2. Hopefully you're catching the common theme here now. And so that means our y equals 2 times 1/3 x minus 2. And then plus 3. So our y equals 2/3 x minus 2 plus 3. And so y equals 2/3 x. So notice you get minus 4/3. Well, that would be 9/3 for 3. So 9/3 minus 4/3 would be 5/3. So plus 5/3. And you can double check to make sure when you plug in those values that we mentioned, it works for this equation too, and we're good to go. So questions on that? So the big thing is starting to recognize, okay, what are these are t to the first power, or what's happening? Now let's make it a little more complicated. Let's say we have a t squared. So this one might look a little funky, but notice we already have pretty much something set up where we could get rid of the t. It just might look a little bit different than what we might be used to, because t equals y plus 1. So that means that x equals y plus 1, the quantity squared, minus 3. So our x equals, well, what the heck is this going to be? Well, y plus 1, the quantity squared, minus 3. Well, let's talk about that. This is, if you notice, we've basically completed the square, but it isn't in the normal context that we're used to. So normal parabola, if I were to say y equals x plus 1 squared minus 3, hopefully we can all graph that. What does that do? That shifts to the left 1, shift to the left 1, and down 3 units. 1, 2, 3. And you get a parabola facing up. Right, something like that. Okay, well, if that's the case, what has actually happened is you have a vertex at -1, -3, right? And this is your graph for this case. But what we've done is we've reversed the roles of x and y. So let's think about what happens. So x and y now, and we want to change it to this equation, right? This x equals y plus 1 squared minus 3. Well, a y plus 1, the quantity squared, that used to be a shift to the left. Well, if we think about in terms of, is it going to be to the left or right, if you kind of reverse this graph on its side, you could think of the left over on this side, or let me rephrase that. In terms of, if you plug in -1 and for the y, where's that going to occur? So it would be when you get down to this point right here. And then we also need the -3 for the x value. So we need something like this. Okay. So notice also, and I didn't actually, this drawing wasn't technically to scale. I should be a little bit more careful. If I'm doing this, I should kind of cross right here and make it a little bit more flat and going so on and so forth, right? And so in this case, what I'm going to need is I'm going to need a parabola to cut through right there, and then kind of coming up over on this point. And this is our graph of x equals y plus 1, the quantity squared, minus 3. Now you can start to see, okay, which direction are we flowing with this graph? Well, let's plug in just a couple values and you can get an idea. T equals 0, what does that give us? Well, t equals 0 will give us -3, -1. T equals 1 would give us, well, in that case, we would get -2 and then 0, right? So our graph is going in this direction. And so we started from over here, and we keep on coming in that direction. So hopefully that makes sense in terms of all these we've been able to replace our parameter. Can we do it in this one? This one looks real scary. Well, the answer to this one is yes in some regards, and that's what we're gonna try and touch on here. So if we did this and kind of worked with a parameter, eliminating it, we could do natural log of x equals t, because the easy way to see that is natural log of x equals natural log of e to the t. And so natural log of x equals t. And I'm kind of pulling a fast one here in some regards, so just be careful. So what's our next bit? So we get y equals e to the negative 2, and then we have natural log of x, right? So that means y equals e to the natural log of properties of logarithms. This is x to the negative 2. So that's y equals, well, let's think about this. E to the natural log, those things are going to cancel away, so you get x to the negative 2, and so y equals 1 over x squared. Okay, so you might think, a natural intuition, 1 over x squared, right? The graph looks like these two volcanoes kind of shooting up here. But let's think about this. X equals e to the t. The graph, oops, that's a little too slow. Goes something like that. So notice if our t's here and our x here, we have the range, the x values are always greater than 0. Ruh-roh. That's not occurring in our graph. So what that tells us is that this whole side has been eliminated. And just to double check to make sure, on the right hand side you can double check and see what that e to the negative 2t looks like. Well, it's going to be something like this. So you have a t and a y value, and you can kind of go from there. So actually our whole graph in this case, notice x starts from something really small for our x values, and it gets really large for our x values. But in the meantime, y is very large to start, and it gets really small. So the only thing you have in terms of the graph is this half of the volcano. Now our drawing, which direction does that occur? Well, remember we started x really small and then we got really large with our x's, so we're going in this direction right here. And so this would be, we do have y equals 1 over x squared, but the one caveat is that we have x greater than 0. So this is y equals 1 over x squared, where x is greater than 0. So that's something to watch out for on some of these where we're going to run into restrictions with the t values. Okay, so keeping that in mind, what actually happens here? Well, recall that this is going to be a circle, and just to illustrate, notice you have x minus 5 equals 2 cosine of pi t, and then y minus 3 equals 2 sine of pi t. Since the cosine and sine of pi t's, there's 2 multiplied by that, so remember you can do the 2 cosine of pi t, the quantity squared, plus y, or sorry, 2 sine of pi t, the quantity squared, and that equals, no matter what t values we plug in between 1 and 2, we're always going to get 4, right? Because you can factor out the cosine squared and the sine squared because it's pi t for both cases. Be careful once again if they're different. It does become something different. But so this means x minus 5 squared plus y minus 3 squared equals 4. Circle, right? Circle centered at 5, 3. Radius of 2. However, here's where we have to be careful. What happens when t equals 1? Well, when t equals 1, what do we get? We get our x value would be 5 plus, well, it would be cosine of pi, 2 cosine pi. Well, cosine of pi is negative 1. So you get 5 minus 2, so your x value is 3 at that point. And then our y value, when you plug in t equals 1, you get 3 plus 2 sine of pi. Well, that's sine of pi is 0, so it's just 3. So you get to 0.33 at that certain juncture. And when t equals 2, what do you get? Well, you'll get cosine of 2 pi in this time. So you get 5 plus 2, and cosine of 2 pi is 1, so that'd be 7. And then in our other case, we get y equals 3 once again. So first off, what does our full circle look like? Oh, I probably need to go a little bit further than that. So let's go 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, and then we'll go -1, -2. Okay, so we're centered at 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. So there's our center. We want to go 2 in each direction. So we'll go here, go there, go there, and then we'll go there. And we're going to draw a circle, but I'm going to draw it really light. And so here's what we know. When t equals 1, we get x equals 3, y equals 3. So that occurs at t equals 1. Our second spot occurs when t equals 2. That's 7, 3. So which direction are we going? Right? Are we going this direction, or are we going this direction? What's happening in those cases? Or have we made a full revolution? You know, and that's easy. You pick a number like, say, 1.5 or 3 pi over 2. And so you'll see, which would give us 3 pi over 2. So 1.5 will give us, or 3 halves, will give us 3 pi over 2. Well, cosine of 3 pi over 2 is 0. So notice you get your x value to be 5. But sine of 3 pi over 2, notice that means that this is negative. So this point down below, right here, would be when t equals 3 halves. And that tells you that this graph, what we get is going in this direction. It only goes once, in fact, and so we can erase that top portion. And that's what our graph looks like. Right. Notice I didn't have to draw it out. You can do the t's and the x's and go about it that way. I strongly encourage it if you're struggling at first, but there's a lot of times we can get rid of these parameters and start to work those things out. So our last problem, let's see how quickly we can work this one out. Well, notice you have t to the first power in both cases. So this, we know, is a line. But it gets even better than that. You will have restrictions on the bounds. So t equals -1. Notice, what does that give us? Well, that gives us x equals 1 plus 3 times -1. So that'd be 1 minus 3, which is -2. And then our y value is 5 minus, it's 2 times -1. So our y value would be 7. Okay, so now when t equals 3, what do we have? Well, you get x equals 1 plus, it goes 3 times 3, which is 9, so 1 plus 9 is 10. And our y equals 5 minus 2 times 3, which is going to be 6, so 5 minus 6 is negative 1. So now the moment of truth. Let's draw this graph. All right, so you see all this extra real estate. 1, 2, 3, 4, 5, 6, 7, 9, and right on the money. There's 10. 1, 2, 3, 5, 6, 7, 8, 9, and just in case 10, and then we can do 1, 2, 3, and then we can do 1, 2, 3. I think we'll be in good shape. Okay, so let's draw the graph. Here's all it is. We know it's a straight line, right? We have 2 points for that line. You have negative 2, 7. So we'll go x equals negative 2, 3, 4, 5, 6, 7. There's 1 point right there. Right? And this is our starting point. Right, because that's the smallest t value. And then we finish at t equals 3. That's x equals 10, y equals negative 1. So we finish right here. Are you ready? On your mark, get set, go. Don't let your eyes fool you. That's a straight line. Done. Right, that's all there is to it. Yeah, we could have figured out exactly where that thing crosses, but the gist is you have a straight line, you have the start, you have the finish, you're ready to go in terms of drawing this thing. So hopefully you've seen how to draw some of those parametric equations, especially with replacing that, and also get comfortable with drawing the 2 graphs and trying to determine, okay, what's going on is the x value and the y value, and we'll work on that some more too. But hopefully this gives you a good start in terms of seeing what's happening. So yeah, if you had any questions, please let me know and whatnot. I just saw you got in here, so if you had some questions, please let me know. Otherwise, we'll call it a night and whatnot. So, and then the next time, what I'm planning on doing is starting to host some reviews for all the material. I'll do parametric and polar curves coming up, and we'll start hosting reviews for all the material for Calc 2, if that sounds good. So I don't see any more questions in particular, so I'm going to call it a night. I hope you have a good one, and I'll talk to you later.